So in exercise 30, if you wanted to double the field strength while keeping the current and turn count the same, what would the coil area have to be? Oh, you know what? I think I have the wrong picture, but it still kind of helps, right? Yeah. It's just picture a bunch of these. it's the same thing. So anyways, in problem number 30, we were reminded that the relationship of the magnetic field around a circular coil is the field is equal to the number of loops times the constant of permeable free space times the current all over 2 times r, where r is the radius of the circle. Okay. And in that particular case, we were asked to, they gave us all the information and asked us to find the current. And so if you work through problem number 30, you ended up with a current of 3.8 amps. And, well, what were all these numbers? Well, if I take this equation, I'm going to do 30 real quick because I didn't want to assign 30. I wanted you to do problem 31, but you kind of need the information. So the radius they gave you was, it ended up being 0.15 meters. The magnetic field was whoops, let me write all this stuff down. The magnetic field that was given to you was 0.8 times 10 to the negative 3 Tesla. I know that's a weird way to write it, but that's how it was. The number of loops was 50, and then the permeable free space constant, remember, is 4 pi times 10 to the negative 7, and this is a weird unit, Tesla meters per amp. And so if you took all of these things and plugged it into the equation, you can calculate that the current was 3.8. So now the question for 31 is if you wanted to double the field strength while keeping the current and turn count the same, what would the coil area have to be? So when we talk about the coil area, we have to make an adjustment because another way that you can write this equation, we've got to think about that. So what they're saying, we don't want to change, so it says, while keeping the current, so I cannot change, right? And the turn count, which is the number of loops, n. So n can't change and I can't change. So I'm going to circle this. This cannot change. This cannot change. This won't change. Okay? And the number 2 won't change. It says, what would the coil area have to be? So now if I want to double B, in other words, I want to take this and I want to double B, and I'll show you how to do this algebraically. I guess I didn't need to write the numbers, but I did. So I have B equals N mu I all over 2R. And now I want to double this number. Okay? If I multiply this side by 2 and I multiply by 2 over here, okay? What I end up doing is I end up having 2b is equal to n mu naught I all over, and this 2 cancels with this r. And so the bottom portion is really like the area. Well, what did I do to the area? The denominator represents the area to some degree. Actually, it represents the diameter. And the diameter of the circle is, you know, so what did I change down here in the denominator? Well, I took, this is the denominator, and I really cut it in half, okay? And so if I cut the denominator in half, what impact does that have on the area? So technically, what I would have to do is to double the field, R would have to be reduced by 1/2. So R would be like 1/2 of what R is, right? If you want to think of it that way. And so the area is proportional. So like the area of a circle, so think of it like this. I'll use a capital R, maybe it'll be better. Normally when we calculate the area of this thing, it would be pi capital R squared. But I have to cut the diameter in half, which will cut my radius in half. So now I'm going to have this thing going on. All right? And so this is how we double the field. But when you calculate the area, you end up with, if I distribute that, I end up with R squared over 2 squared, which is really pi R squared divided by 4, which could be rewritten as pi 1/4 times R squared. So then you would reduce that by 1/4. So you would need to reduce the area by a factor of 1/4. And that's it.